This video will be about recursive formulas. Up until now, to describe all of our sequences, we have been using explicit formulas, or formulas that give the nth term in terms of n. An implicit formula, or a recursive formula, in contrast, gives a formula for the nth term in terms of preceding terms of the sequence. So this usually looks like a of n plus 1 equals c1 an plus c2 an minus 1 plus c3 an minus 2, etc., where c1, c2, c3, etc. are constants. We can write recursive formulas for arithmetic series. To do this, let's look at a sample series. Let's say that it starts at 2, and we're going to add 3 to each term. Now, our explicit formula for this sequence is a of n equals the first term plus n minus 1 times the difference, or 3n minus 1. And so we can see that this formula is in terms of n. Now, what if we want to make a formula that relates each of the terms to the terms preceding it? Then we can see that all of these terms here are equal to 3 plus the preceding term. So that means we can say that a of n plus 1 equals a of n plus 3 for n greater than or equal to 1. And that means if we plug in n equals 1, then what the formula tells us is that a of 1 plus 1, or a2, equals a1 plus 3. And if we're given that a1 equals 2, then from this formula we can find out that a2 equals 5. Similarly, we can plug in n equals 2, and what that tells us is that a of 2 plus 1, or a3, equals a2 plus 3. And so if we already know what a2 is, then we know that we can just add 3 to get a3. We can do something similar for a geometric series. Again, I'll write a sample geometric series so we can look at it as an example. We'll start with 1, and we'll just multiply each of the terms by 2 to get the next one. That means that our explicit formula is gn equals 1 times 2 to the power of n minus 1. Again, this is in terms of n. And if we wanted to put it in terms of preceding terms, then we could say that g of n plus 1 is equal to the preceding term, g of n, times 2, for n greater than or equal to 1. So now if we plug in some sample values of n, then we end up with statements like g2 equals 2g1, g3 equals 2g2, etc. But notice that there's no value of n that we can plug in that will give us a formula that tells us what g1 equals. So in our recursive formula, we have to specify our g1, say that this equals 1, in order for our formula to work. One thing to note is that so far, we've been writing things like an plus 1 equals an plus 3. But note that this is the exact same formula as writing an equals an minus 1 plus 3, and same as an minus 1 equals an minus 2 plus 3. Because the only thing these recursive formulas tell us is that we're going to add 3 to a previous term to get to the next term. The differences between writing these formulas is that for the first one, we want to start at n greater than or equal to 1. The second, we would have to start at n greater than or equal to 2. And the third would start at n greater than or equal to 3. Otherwise, if we wanted to plug in something like n equals 1 into this third formula, what we would end up with is a0 equals a negative 1 plus 3, which doesn't make any sense. Let's say we have a function f of x. We can do something called iterating it. That means that we'll take some initial value xo, we'll plug that into our function, get f of xo. And so the first number that we get out is called our first iterate. Then we'll take whatever value we got from plugging that in and plug that into our function. So f of xo is called our second iterate. Similarly, f of xo is our third iterate. And we can continue this pattern to find any nth iterate of f of x.